Okay, here I'm. Okay, can you hear me, guys? Now, yeah. Okay, I think you can hear me now. Uh, Rest of you, can all of you hear me? Yeah. So, all right. So this particular note is already available in the class notes section of the Cheenta. So I'll just go ahead and share that screen with you guys so that you can actually check it out. So if you are not part of the Open College Math portal, I would strongly recommend you to join it, because we will keep on posting this particular, yeah, we'll keep on posting resources in this particular portal. Okay, so make sure to join that. All right, so now that we understand all of this stuff, let's get into the actual business of doing mathematics, and let's share the screen. Okay, yeah, I will be sharing the link of the portal. Yeah, sure, in a moment. So I'll just start broadcasting. 1 second. Okay. All right. I'm assuming that you can see the screen, all of you. Yeah. Okay. Okay. So, as discussed earlier, we will be talking about some introductory ideas in group theory. You know, the great thing about group theory is this, that the definitions and the initial ideas are really simple. The definitions and the initial ideas are really simple, but when you start applying them in problems, that's where people get stuck. Okay, so the method that we will be using today, and it's usually used in other Cheenta programs as well, is that we go from problems to concepts. Okay, so this is a standard strategy that we use. Go from problem to contest. So we will right away start with a problem, and then we will discuss some of the concepts that are useful to solve that problem. So let me go ahead and give you the first problem that we will be working on. And even if you don't know anything about group theory, do not worry, we will explain everything and it will be very clear. So here is the problem that we will start with. The problem is this: if every element of a group G is its self inverse, then show that G is in fact an abelian group. Okay, so if you do not know anything about group theory, don't worry about it. Let me explain a couple of words, and if you know something about group theory, then go ahead and try to prove this. Okay, so let's look at the word group first. If you are looking at this for the first time, there is a very standard definition of what is a group G. So firstly, it's a set. A group G is a set with a binary operation star. So basically, if you have two elements A and B in the set G, so as I said, G is first and foremost a set. If you have two elements A and B in the set, then you can actually create A star B, another element of G, and A star B will be and the fact that A star B is an element of G, as the fact that A star B is in G is known as closure property of the group. Closure property of the group. That is, we usually say multiply, or you can say combine. So combine two elements of the group, you get another element of the same group. That's how this is known as the closure property. And then there is another thing that is there in a group G. uh, for a, there exists an identity element, E in that set G, such that A star E is equal to E star A is equals to A. So identity element does not change anything, it preserves the group element. And finally we also have the inverse. There exists inverse of each element A in G, which basically means that for A there is A inverse such that A star A inverse is equals to the identity element. That's the definition, that you multiply the number with its inverse, you multiply the element with its inverse, and you get the identity element back. And one more thing, so here is the second property is identity element exists. Third one is that the inverse exists. And finally, the star operation is associative, which basically means that A star B star C is equal to A star B star C. So the order does not matter, in which the order in which you do the operation. Now that we understand the basic definition of a group, let's get back to this problem and see that if we can understand all the words in this sentence. If every element of a group G is its self-inverse, so basically if you take, so G is a particular group that has a very beautiful property. In this case, the group G has a very beautiful property. And what is the property? The property is that A, if A is in G, then A star A is identity. Now I'll tell you a very interesting fact here. This is a kind of a situation that sometimes makes group theorists very uncomfortable. These are sometimes known as torsion elements. So if you have seen the word torsion before, now you know that torsion is basically an element of a group which when raised to some power gives identity. Okay, so infinite groups in particular, if they have torsion elements, then sometimes group theorists can become very uncomfortable with that. Okay, Devjit, go ahead.
Sir, can you please repeat the torsion element? I didn't get that correctly.
Yeah, it's just a
Thank you,
side
sir.
note that if you take an element, if you take any element of the group and you raise it to some power and becomes 1, then that particular element is sometimes known as a torsion element. Okay, A
Okay,
torsion,
sir. Thank you,
a
sir.
torsion element. Yeah. So here, of course, what you are seeing is that every element is a torsion element, right? And what is the power to which, if you raise it, you get 1? What is that power that you are seeing for every element? A to the power what is 1,
Uh,
or identity in this particular case? Well, in this particular case, it is exactly the number 2. Exactly. Well, yeah, k is greater than 1, you can say. Of course, you're right. Of course, if k is equal to 1, then doesn't make sense, right? It's not very interesting, because in that way every element is a torsion element for every group. Yeah. In Koustav is right. Finite groups have in finite groups every element is a torsion element. That's correct. You are absolutely right. So, but this is a very curious scenario where every element of the group G is a self inverse, in the sense, if you do, sorry, yeah, Arbas, in this is the condition given in the problem actually. The problem says that the every element of the group G in this particular case is a self inverse. Not always. In this particular case, in this particular problem, it is a self inverse. Okay. And with that condition given, with that condition given, we want to show that G is an abelian group. So anyone has an idea how to go about doing this problem? Okay, Gautam has an idea. Okay, Gautam, how do you go about this problem? Tell me. Okay. So the given data is this, that G is a group if A is in G, then A square is equals to identity. That is given. What do we want to show? We want to show that G is abelian. What does that mean? It means that A star B is equal to B star A for any two elements in that particular group, right? Okay, see, Gautam has a very nice sort of proof that's going on here. Okay, let's see what he's saying. He's saying, okay, take any two members A and B. Let's look at the inverse of A and B, because obviously we are given that AB is self inverse. So if I take the inverse of AB, if I take the inverse of the element AB, you have to think of A times B as an element of the group, because by the closure property that will be true. So take any two elements A and B from the group G. Take any two elements A and B from the group G and consider the new element, the possibly new element, the element A times B. That's also a member of the group G. Given by the given property, by the given property, A times B is same as the inverse of A times B. That we know, because every member of the group is a self inverse. We know that, certainly. So what can we say? Well, there is a very powerful but simple formula of inverse of two numbers. that AB inverse is B inverse A inverse. So this is something that we need to use here. So let's understand this part first. So let's understand this. Why is this true? Why is AB inverse is equal to B inverse A inverse? Okay, let's see. AB inverse, what does this thing mean? This is something which, when multiplied to AB, gives identity. That's the meaning of the symbol AB raised to the power minus 1. It is an element which, when multiplied to AB, gives me identity. I just need to check whether the right hand side element is such an element or not. Does this element satisfy this property, this condition? That is what we have to check. That is, if I multiply with AB, B inverse A inverse, will I get identity? Let's see. Of course I will, because B times B inverse, this is identity. A times identity is A, and A times A inverse is identity. So certainly this is the AB inverse is clearly B inverse A inverse. That's a very simple but powerful tool that we use all the time. Okay. Okay. So now that we have this, let's write it here. So in the first step, we know that AB is equal to AB inverse because the element AB is self inverse, that's given in the problem. So let's keep that in mind. Given, and this is the derivation, we expanded AB inverse. Now B inverse is B. Why is that? Because B inverse is self inverse, right? So B is every element is equal to its inverse, so B inverse is B, and A inverse is A, so AB is equal to BA. That's what we wanted to show, because that's the question, whether this is commutative or not. And it is commutative. We started with any two elements A and B. We showed that it is equal to B times A. See, this is a very simple example of a group theory problem. We just use the little ideas, little definitions of the of groups, and we use the properties given in the problem, and we sort of unravel the entire thing. This is typical of group theory. We always do certain things like this. Okay, so some of you were asking this before the session for today. Yeah, this is quite nice actually. This problem is from Topics in Algebra in Herstein. Herstein is a very beautiful book. It's a bit tough, I guess, but it's quite a beautiful book. So I'll write the name of the book, Topics in Algebra by Herstein. Though I do not suggest to that you follow this book at the beginning. You should start with Gallien's Contemporary Abstract Algebra, and then you can go to the. So those of you who are not internal students, some of you were asking me before the class. So just to mention that, from September 1, there is a group theory program starting for 3 months. You can check out the link in the Open College portal if you want. Okay, let's go ahead and try the next problem that we have in the list. So the next thing is actually like this, that problem 2. Remember, our strategy is the following. To learn group theory, what we are trying to do, we are starting with a problem, understanding certain concepts associated with it, and then trying to solve the problem. So, problem to concept is a standard strategy that works quite nicely in this level of mathematics. So, let's look at this problem. This is problem number 2, and it says that it's a construction problem. It's a construction problem. So, what it says is, for any n greater than 2, construct a non-abelian group. Construct a non-abelian group of order 2n. Okay, construct a non-abelian group of order 2n. Yeah, so dn is definitely one example that you can use, but we need a generic construction in the sense. Okay, so Titi is saying Sn. Well, we have to see to that. How many members are there in S4? How many members are there in S4? Anyone? If you are familiar with these type of groups, maybe you can.
4 factorial.
Correct. So those of you understand what group S4 is. If you don't understand what is S4, don't worry about it. It's a name of a type of group. It's very simple. It's a permutation group of 4 elements. But it's if you don't know, that's fine. If you know it, you know that there are 24 elements. So in S4, so Sn in general wouldn't work. S3 is a particular case that would work. So how many elements are there in S3? Well, S3 is 3 factorial, which is 6, which turns out to be twice of 3. It's kind of an accident in some sense, right? Okay, so one of the things that we would like to learn is what is the meaning of non-abelian. So guys, try this particular problem if you know what is the meaning of non-abelian. If you don't, then here it is. Remember, G was a set. G is first and foremost a set with a binary operation star. So I have a bunch of elements here. When I write 1, 2, 3 like this, I must say that I am just saying that the group is countable. There are many examples of groups which are not countable. But anyway, let's not worry too much about it for the moment. So A1, if I can find two elements, AI and AJ, such that AI star AJ is not equal to AJ star AI. If that happens, we say that the group is non-abelian, not commutative. We are not asking this for every pair of elements. Be very careful about it. There can be two elements such that AB equals to BA happens, even in a non-abelian group. That can happen. But we are just saying there is at least one pair of element where this does not happen, Okay, so that's what this set G is all about. Non-abelian group G is all about. So we want to create a non-abelian group of order 2n. Order, what is the meaning of the word order of a group? Well, it's very simple, is the number of elements in the group, is the cardinality of the set G. So why don't they say just cardinality? I don't know. They should have. They could have maybe. Okay, so that's fine. So we understand what the order is. Now let's look at the problem one more time. For any number n greater than 2, we want to construct a non-abelian group of order 2n. A non-abelian group of order 2n. That's what we want to do. So we want a general construction, but before we do that, someone just mentioned dihedral groups here in the DNA. Postov mentioned it. So let's look at that. So dihedral group. So it's basically the group of symmetries of a figure F. So can anyone just tell me what is the meaning of the word symmetry? Is there anyone who can explain to me what is the meaning of the word, the precise meaning of the word symmetry? Because symmetry comes up everywhere. Okay, symmetry is an action which does not change a certain property of an object. Okay, so okay, that's quite a general kind of a thing, but that's true in fact. So but that particular word has a sentence, has a lot of words that we need to unpack. For example, the word action is there. We don't know what that means at the moment, at least. So Gautam is right in the sense that to understand symmetry, we have to first understand a notion in our context, the thing that we are trying to do for the moment. We have to understand something called isometry first. It's a related idea. Now, don't think that they are same. They are not same. Can anyone give me an example? Can anyone give me an example of an isometry that is not a symmetry? An example of an isometry that is certainly not a symmetry. Can anyone give me example of that? Okay, so there are actually, so I'll first explain what is isometry. So let's look at the definition once. So suppose we have a space. Let's talk about R2 for the moment. R2 is the familiar Euclidean plane, is the XY plane, if you may want to think about it like that. Actually, when I write it like this, XY plane or something, if you want to think of it as a plain sheet of paper, you are actually putting more structures on R2. Here is a very important way to think about R2. Let's look at what R2 is and what E2 is. There is a conceptual difference between R2 and E2. Sometimes kids miss this, so let me spend a minute on that. Suppose you take a piece of paper, you take a plain sheet of paper, you make small grains out of it, you tear it down into atomic pieces. Okay, you may have small dust, you have sort of broken it down and made it into dust and poured it in a in a in a bowl. So what do you have in that bowl? The little particles of the paper that you have in that bowl, that is what you should think when I say the word R2. So R2 is just dust of particles on your paper. So when you think of R2, do not think of it like a plain sheet of paper, because when you are thinking in your mind, when you are using your imagination and making it a plain sheet of paper, you are actually applying additional mathematical structures on this dust particles. And what is that additional mathematical structure? Well, you are actually putting a distance function on it. You are giving us a recipe on how to compute distances between any 2 points on that, in that particular set. So in particular, when we specify the distance function, we say that it's E2. E2 is like the general metric. So the distance function, so if I have 2 points x1 y1 and x2 y2, if I have 2 points, then the way to compute the distance between the 2 points is square root of x1 minus x2 whole square plus y1 minus y2 whole square. So I am explicitly giving you a method of computing the distance from A to B. Once I give you that recipe, I've actually, now I have a plain piece of paper in some sense. Okay, so then you can think about, why is your paper not sort of curved? Is there a hidden idea of curvature that is hidden in this particular distance function, that it's not curved? And what does curving even mean? So anyway, all those things are there. Now suppose we are, so those things are very exciting and you can think about it. But for the moment, let us focus on the problem that we have. We were defining isometry. So an isometry is nothing but is a function f from, let's write E2 to E2. Now you know what I mean by E2. E2 is just a set R2 with a distance function, right? A function from E2 to E2 such that such that should I write E2? I don't know. Any distance function would work actually. Any metric space, any distance function would work. Let's keep it E2 for the moment, okay? Such that if you take A and B, if A and B are 2 points in E2, then the distance from A to B is equal to the distance between FA and FB. That is, after you apply the function where they go, if you compute the distance between the images, well, you get the same distance. It's a very simple idea. The function is preserving the distance. The function is preserving the distance. So if you have A and B as 2 points on xy plane, suppose after applying the function, this is FA and this is FB. These are the two image points. If the function is an isometry, the distance between A and B and the distance between FA and FB are equal. That is the meaning of the word isometry. Okay, so that's great. Now the question is, what is a symmetry? A symmetry is an, let's work with symmetries in R2. A symmetry is a map from R2. Let's make it E2 to E2. Let me put a super warning here actually. Super warning. I'm actually working with a very special definition. You should actually think about it more in lines of what Gotham actually said. It's a more general kind of setting, but for the proper, when people think about isometry, they are always thinking about this actually. So a symmetry is a map from E2 to symmetry of F is a map from E2 to E2, map G from E2 to E2, such that G is an isometry and GF is F. In other words, it's a distance preserving map such that the image of the object F, so F is here, F is some subset of E2. Okay, so if you take a subset of the plane, let's say a triangle, maybe a triangle is an example of a subset, an equilateral triangle maybe. So if you take, this is your F, this is the F, so it's a map from the plane to the plane. The map's name is G, and G is an isometry, so it preserves distances, and the image is also the same thing as the object. That is what a symmetry is. In our context, we will be happy with this. There are more complicated definitions of symmetry. We are not going to talk about it at the moment. Okay, so here is a beautiful problem that you can think about, and it is also in the class notes actually. Show that any isometry from Rn to R, forget about Rn, R2 to R2, let's say E2 to E2, is always a continuous function. You see how we are moving between analysis, that is, let's say calculus, let's not say analysis, how we are moving between calculus and these type of functions which are distance dependent, and we will show that these symmetries are actually forming a group, which one of our friends have rightly pointed out is, who said that, Kostav or someone said that it's called DN. I mean, it's a special type of a group which are looking at symmetries of certain very special figures like triangles, squares, and so on. So for example, if you look at an equilateral triangle ABC, if you look at an equilateral triangle ABC, what do you get? Well, let's look at the symmetries of the equilateral triangle. So this doesn't look like a symmetry, sorry. I'm sorry, doesn't look equilateral. So this is a ABC equilateral. So a symmetry, one example of a symmetry is a reflection about the median AM. So a reflection about median AM. You reflect it, you get back the triangle again. The only difference is B goes to C and C goes to B. So the points are moving around. Understand this very well. The points can move around. In fact, if something interesting has to happen, the points better move around. Okay, so points move around. That's great. Distance between points and their images are preserved. So A is sent to A prime, B is sent to B prime. So the distance between AB and A prime B prime is also preserved. Of course it is. Of course it is. But the entire object ABC sits on itself. The image sits on itself. So reflection about the median AM is an example of a symmetry of the triangle ABC. And in fact, one can show that the set of all symmetries of equilateral triangles is a group. So this is something that's it's a good example of a finite group, and you can definitely study it. And Kostaps gave us a name of this particular group. He says it is this. I'm a little confused though. Should I write it dn or d2n? Some books say dn, some books say d2n. It's the same thing actually. So this is sometimes known as the dihedral group. Okay. Okay. Now let's get back to the problem. So we have, okay, so one more thing I would like to point out. I mean, I love isometries so much because, in fact, whenever people start talking about linear algebra, if you start a course in linear algebra, I think the first thing someone should discuss and understand is about isometries. Okay, because they are very well related to certain parts of linear algebra like linear transformations and stuff like that. Okay, now let's get back to the problem that we were doing. We wanted to construct, for any n greater than 2, we wanted to construct a non-abelian group of order 2n. Okay, anyone has an idea about how to do this problem? A generic construction is warranted here. So here is a generic construction. So generic construction. This is of course due to Herstein. But if you think about it, to be very fair, if you think about it for some time, you can definitely figure it out, because it's not this part is at least not rocket science. So what we do is we go ahead and do it like this. We say that suppose we take any set G, we want to so what is it that we have to do? We have to write down 2n elements, write down 2n elements, and say how they multiply out. Okay, okay, so let's do it like this. So let's say that we have the identity element. Of course, identity element is definitely there. And then let's say there is one more element which is not the identity element. Let's say a. Okay, and we have a bunch of powers of a, such that a to the power n is maybe identity back again. So we can always do that. So a is square a cube a to the power n minus 1, because if I write a to the power n, it will be identity again. Okay, now what Well, this is quite beautiful actually how Herstein does it. So we have another element b such that b square is identity. We take another element b such that b square is identity. So what do we want? We don't want a and b to commute. Here is what we want. We do not want ab equals to ba. We don't want this. Why do we not want this? Because if this happens, then this becomes identity. This becomes identity. So to do that, we will be using a very sort of an interesting kind of a method. We will be replacing it. Let's multiply b inverse on both sides. So we want, if this happens, this is what we do not want, right? So what we will do is we will create a rule. We will create a rule by ourselves. We'll say, okay, we don't want this one to be a, let's have this one equivalent to a inverse. This is the first example of a relator in group theory. If you know generators and relators, then you know that this is an example of a relator that I'm creating right now, or Herstein is creating right now. If you have not seen this before, the word relator, don't worry about it. When we talk about relators, you will remember this and you'll say, okay, this was good. Okay, so this is a rule. This is a rule that we created. This is a rule that we created. No one else created this rule. We created it, and we can do anything we want as long as we are playing the game with the rules of the definition of the group. That's sometimes that's why people call it a group craft. Group theorists are craftsmen who are creating new stuff. Okay, so far what do we have? Oh, there is one danger. One danger. What if a is equal to a inverse? Then our trick won't work. But that's fine because we are working with n greater than 2, right? We are working with, oops, sorry. We are working with n greater than 2. So we can assume that a square is not equals to identity. So a square is not identity. So you have to be always very careful. So now with this information as a homework, as a homework, try to construct the remaining unique elements of G, and observe that there are only 2 n elements that can be created like this. Okay, so that's for today, everyone. Thank you for attending. Bye, all of you. Take care. Yes, Devjit, go ahead.
Sir, can you please recommend some good books on algebra on for TIFR?
Yeah, I think the one of the best books that you can start with is definitely um, the Galleon. What are you studying, Devjit? Can you tell me a little bit about your background?
Yes, I graduated on 2020, BSc graduate.
Okay.
And I'm looking for TIFR. So I was from a physics background, but I want to do my integrated PhD or research work on mathematics.
Okay.
So and TIFR, the eligibility criteria all are satisfied for me. and that's why I am looking for that.
I would say, Devjit, you focus on Galleon first, okay? And then
Okay.
that's number one. Number two, you focus on the past problems in TIFR. That's number two. And then, if you have time, then go for Herstein. In Herstein is a very good book, but it can be really tough. Some problems are really challenging. So, because they are kind of twisted, and TIFR does not ask that twisted problems in group theory, in fact. So, yeah, number theory actually, if you are enrolling for an M.Math program at Cheenta or the college mathematics program, we always recommend the students to attend the normal non college pre college level classes as well, like with the BMAT people. Sometimes the students do, sometimes they don't, but we strongly recommend it, and it's included in your course, so you should certainly attend it. There is one extra class every week devoted toward this number theory, combinatorics, geometry, and all of those stuff.
Okay,
Okay.
sir. Thank you. And what about sir analysis? For TIFR?
Books in analysis. So
Yes.
analysis is,
Yes.
so analysis is this, like this. The stuff you need in analysis, of course, you need a strong background, but I don't think Bartle and there is nothing. But I think Bartle and Shepard is good. You know, yeah. So I'll give the link actually. Where is the link? Yeah. So here is the link in the chat. Here we go. And I can also put the
Okay,
link
sir.
here.
Thank you, sir.
Yeah. So, as I said, Bartle and Shepard is good, but if you really want to look inside the mind of a genius, you can look at Terry Tao. Tao's analysis is really good. But the problem with this is that, you know, there are so many good books that people can get really confused, and no book is really complete in the sense each book has its advantages and disadvantages. I would strongly suggest focus on one book first, like Barton Shepard, any book. Barton Shepard is really good because it's kind of elementary, and then focus on the problems of the contest. And then, if you have more time, then you can go for Tao is there. There is a very good problem book set by Kakzor. This is called, I think, Problems in Mathematical Analysis. Kumar San has a very nice book called Topology of Metric Spaces. It's a very nice book in the sense that it covers the material with in a problem driven manner, kind of the way we did today. So that's a very nice book. But start with one book. Bartlett Shepard is good. Just get it done. Okay, any more questions? Anyone? No? Okay, thank you for attending, all of you. Good night. Bye.